Hello everybody. At the end of the last lecture I gave you this task of finding the reachability matrix of a graph, and I promised that I was going to upload a new video with the solution. Okay, so this is the video in which I'm going to compute the reachability matrix of this graph. Okay, so notice that here I have already written the adjacency matrix of the graph. We have um, an edge from 1 to 2, an edge from 2 to 3, an edge from 3 to 1, and edges from 4 to 1 and from 4 to 2. Those are the ones in the matrix. Okay, and we know that of course m to the power 0, which is the uh, zero reachability matrix, is the identity matrix. Okay, so it's ones in the diagonal and zeros everywhere else. Okay, so this is the identity matrix, the zero reachability matrix. This is of course M1, the one reachability matrix. In order to compute M2, remember that we need to perform the multiplication m times m. Okay, so I'm going to copy here the matrix m twice, and I'm going to do this computation. Of course, you can do this computation with the usual algorithm for multiplication, but I'm going to show you that since we are dealing with Boolean matrices, this can be a lot quicker. Okay, because notice that, well, to fill in this element here, we need to use this row multiplied by this column. Okay, that is what we need to do. So it would be 0 times 0 plus 1 times 0 plus 0 times 1 plus 0 times 1, which is 0. Okay, but notice that since all the elements are Boolean, we only care about the ones in this row. So we are going to multiply all the other elements by 0 and only the elements in this row by 1. Okay, so the other ones, we know that they are going to be 0 because we have zeros here. 0 here in the first position, 0 here in the second position, 0 here in the third position. Okay, so we only care about the ones there, and that one is going to multiply first this column. This row is going to multiply first this column, then this column, then this column, then the fourth column. Okay, but all the time we are with the same row, so we are only going to multiply the one for the elements in this row here. So when we multiply the matrix by this row to find the first row of the square, we only care about this one that is going to select this second row here. So you can easily check that the result in the first row is exactly the second row in the matrix, because we have a 1 here in the second position. So what we get here is 0, 0, 1, 0. Okay, and this is consistent with the interpretation that we gave to the squared of the adjacency matrix, because it's going to give us the paths of length 2 that start in 1, and the only path of length 2 that starts in 1 is this one that uses this edge and this edge. Okay, so it goes from 1 to 3, and that is exactly what we get here in this position. Okay, so let's do the same but a bit quicker now for the second row. Okay, So this is 0. Let me erase this. Now we are going to multiply this row here times this column, then this column, then the third, then the fourth. Okay? And again, we only have one in the whole row, so we are going to select, let me do it a bit better. We are going to select this row here because we have a 1 here in the third position, and that is the one that is going to multiply the elements in the third row of the matrix. Okay, so we are going to obtain here 1 0 0 0 0, and that is consistent with the interpretation of the square of the adjacency matrix as the 2 reachability matrix, because if you check in the graph, we have a path of length 2 from 2 to 1, and that is the only path of length 2 that we can get starting in 2. Okay, let's do this a bit more quickly now that we know how to do it. So here for third row, we select the first row of the matrix, that is 0 1 0 0. Okay, and for the 0 0, let me erase this. Okay, and for the fourth row, notice that now we have 2 1s, so we need to add the first and second row. Okay, we need to add this row with this row. This is consistent with the interpretation of the square of the matrix as the 2 reachability matrix, as the matrix that gives us the paths of length 2, because what we are doing when we start in 4, now we are in row 4, so these are the paths that have length 2 and start in 4, is to either go to 2 or go to 1. And if we have edges from there, then we can join the edge from 4 to 1 or from 4 to 2 with the new edge that we find in 1 or 2 and form paths of length 2. Okay, so that's why we have to compute the addition of rows 1 and 2. Okay, and then what we get is 0 1 1 0. That is the addition of the first 2 rows. So this is the matrix of paths of length 2, the 2 reachability matrix. This is much easier to compute than trying to take a look at the graph and finding all the paths of length 2, because you can miss some of them, and if the graph is bigger, then it's more complicated and it's easier to miss some of the paths. So let me copy this matrix here. We are going to need this matrix. Let me erase the computation, but copy the matrix here. Or, well, I will write here M2. Okay, so now M3 is going to be computed as either m times m square or m squared times m, as you wish. Okay, so let's do, it's normally easy to do m times m squared or m2, because m usually have less ones. Okay, so when we select the rows, then it's easier to do that. Okay, so but it doesn't matter, it's the same result. Okay, so now m3 is going to go here, and it's going to be this m times m2. So we are going to first select the second row of m2. We have a 1 here in this position. Okay, and that means that we need to select the second row in this matrix. Okay, so we are going to write here 1 0 0 0. And notice that this is consistent with the interpretation of the matrix as the matrix that gives us the paths of length 3, because in the graph, if we start in 1, we can go to 2, then to 3, and go back to 1 with a path of length 3. Okay, for the second row, we have a 1 here in the third position, so we are going to select this third row here. So this is going to be 0, 1, 0, 0. And for the third row, we have a 1 in the first position, so we select the first row of matrix M2, so 0, 0, 1, 0. And for the fourth row, we have two 1s in positions 1 and 2, so we need to add rows 1 and 2 of the second matrix, of matrix M2. Okay, so this is the third matrix. And remember that now we can stop. We can stop here. We don't need to compute M4, because any path of length 4 or more can be reduced to a path of length 3 or less, which starts and ends in the same vertices. Okay, and what we are interested in is whether we can reach a vertex from another, and not on how many paths or the length of those paths. Okay, and now to compute, let me erase something. What can I do? I'm going to copy here M2. I'm going to copy here M2 to have some space at the bottom of the whiteboard. Okay. So now what we need to compute is the addition of these four matrices, starting with M0 and then M1, M2, and M3 to get the reachability matrix, what we call M infinity. Okay, so the reachability matrix, let me do it. Oh, okay. The reachability matrix M infinite is the addition of all these matrices. Okay, so whenever we find a 1 in a position in the any of the four matrices, there will be a 1 in that position in the reachability matrix. We perform the addition, but remember that this addition is a Boolean addition. So if we get a number that is bigger than 1, then we transform it into 1. We are not interested in the total number of paths, but only if whether there exists a path or not. If there are many paths, we reduce that to a 1. So for instance, for position 0, 0, notice that we have a 1 here and a 1 here. So 1 plus 1 is 2, of course, but we reduce it to 1. Okay, so we get a 1 in position 1, 1, 1. We also have a 1 here in position 1, 2 of this matrix, so we also get a 1 here. We also have a 1 here in this position, so we get a 1 here. But the other element in this row is going to be 0, because all the elements in all the four matrices have a 0 there. Okay, so this is going to be 0. Similarly, for the other rows, please check that you get 1, 1, 1, 0, 1, 1, 1, 0, and for the fourth row you get 1, 1, 1, 1. Okay, so this is the reachability matrix for this graph, and what we learn from this reachability matrix is that first, the graph is not strongly connected, because if it were strongly connected, then we should have 1s everywhere. And these zeros here are telling us that if we start from either 1, 2, or 3, we cannot reach 4, something that is clear in the graph. But imagine that we have a graph with 4,000 vertices. Okay, it's not so easy to notice this kind of thing. Okay, so what is the matrix is telling us is that the graph is not strongly connected, but it's also telling us that we have here a strong connected component, because here we have a submatrix that is completely formed by ones. Okay, if we had no if the vertex 4 were not in the graph, then the graph would be connected. Okay, so the graph formed only by vertices 1, 2, and 3 is strongly connected. Okay, that is a strong connected component of the graph. And of course, the other connected component, the other strongly connected component of the graph is 4 by itself. Okay, because 4 is connected, of course, it's reachable from itself, but no other vertex can reach 4. Okay, so this is how you compute the reachability matrix of a graph, and in this case we obtain the result that the graph is not strongly connected. I hope you have understood how to compute this reachability matrix, how to make the computation faster, taking into account that we are doing Boolean operations. And if you have any question or any doubt, please use the discussion forum or send me an email to ask me anything that you didn't understand. This is the last video before the Easter holidays. I hope you are safe and well, and please try to watch the videos that you have not watched yet, and if you have any question, send me an email or use the discussion forum, and we will have new videos after the holidays, and we will have also a Microsoft Teams session for you to ask me any question. Goodbye.